As you might already know, questions are the backbone of scientific investigations. What do plants need to grow? What proteins control cell division? How are traits inherited? Most questions about the natural world can be answered by collecting scientific data in experiments. Scientific data isn't just observations about a phenomenon, it's information gathered from experiments that are carefully designed to test one variable at a time. Prior to starting an experiment, it's important to have a hypothesis based on background research. A hypothesis is an educated guess or prediction about what your experiment will show. Hypotheses usually take the form of if then, because. If I change something, then something will happen because. After you collect your data, it's important to analyze your results and then go back to compare them to the hypothesis. But how exactly do you analyze data? What should you look for to support or refute your hypothesis? Scientists focus on 3 ways to analyze data: looking at trends, looking at patterns, and looking at relationships. To understand these forms of analysis, let's look at an example of each. One of the most important ecological topics today is climate change. Scientists have been studying how surface temperatures have changed over more than 100 years. Every year, there are some days where there are abnormally high temperatures and abnormally low temperatures. The data can be plotted as a scatter plot, where a dot is included for each temperature recorded, although some days are high and some days are lower than average. Overall, the temperature is increasing each year. This is a trend, the general tendency of a set of data to change. The data points may vary slightly, but overall, the data moves in one direction. In the case of global warming, there is a trend of temperature increases over a long period of time. Climate change skeptics will argue that there are still cold days, so global warming can't be happening. But when we examine the scientific data, we can see that overall, the trend is that global temperature is increasing. Patterns in science are a little different. Data doesn't have to follow a trend, always going up or down over time. A pattern is when data repeats in a predictable way. A good example of a pattern in science comes from the father of genetics, Gregor Mendel. Mendel was a scientist in the 1800s who studied the genetics of pea plants. He would breed pea plants with different characteristics and observe how these characteristics showed up in the next generation. When he bred a purebred yellow plant with a purebred green plant, he noticed that all plants were yellow. This data showed up with other traits as well, such as plant size, pea pod shape, and flower color. One trait would mask the other. Mendel noticed this pattern in his experiments. This led Mendel to propose the idea of dominance, that some traits mask others. This is the common mode of inheritance, and explains many traits in humans, such as eye color, ear shape, and hairlines. Relationships are similar to trends, except that the data have a clear mathematical relationship. Let's look at an example. In your physics lab, you're examining the relationship between mass and force. Each time you apply a different mass to a spring scale and measure the force. When you apply 1 kilogram of mass, you record a force of 10 newtons. When you apply 2 kilograms of mass, you record a force of 20 newtons. Your data continues in this way for the remaining masses you weigh. From your data, you conclude that for every 1 kilogram of mass added, the force measured in newtons increases by 10. This is called a direct relationship. When one variable increases or decreases, the other variable does the same. The data fits the formula for Newton's second law. Force is equal to mass multiplied by acceleration. F equals ma. Sometimes one variable has the opposite effect on the other. When studying motion, you measure how much time it takes for carts moving at different speeds to travel 1 meter. When you use a greater velocity, it takes less time for the cart to travel the distance. This is called an indirect relationship. When one variable goes up, the other goes down. So now that we can identify trends, patterns, and relationships during our data analysis, what do we do with that information? After any scientific investigation, you need to return to your hypothesis. First, refresh your memory on what you thought would happen. Next, go to your data and any trends, patterns, or relationships you found. Do these match what you predicted? Were there any discrepancies? If your data matched your hypothesis was supported. You can go on to repeat the experiment to improve the reliability of your results, or proceed forward with further questions on the topic. However, sometimes our data refutes our hypothesis, meaning it does not match what we predicted. What do you do in this situation? First, check again for trends. It might seem that your data doesn't fit your hypothesis, but look at the overall direction of your data. If it definitely doesn't match, think about another explanation of what you're seeing. If your data didn't support your hypothesis, it doesn't mean your experiment is wrong or bad. All it means is there is another scientific phenomenon happening, and it's your job to design a new experiment to find out what it is. Scientific data is gathered from carefully designed experiments based on background research and a hypothesis. After data is collected, it can be analyzed by looking for trends, patterns, and relationships. Trends are general directions of data, such as an overall increase in global temperature. Patterns don't necessarily involve data going one way or the other, but rather describe a repeating observation. Relationships are like trends, but involve a mathematical relationship, such as force and mass, based on Newton's second law. Relationships can be direct, where both variables increase or decrease, or indirect, where one variable increases as the other decreases.